Well, not a whole lot we know what to do with when it's in the log part of the world there. So maybe we could rewrite it as an exponential. What would that be as an exponential? X squared is equal to 16 over 9. Perfect. Now, do we know how to solve that kind of problem? How you get rid of x squared? Nope. Take the square root, right? Plus or minus in front of the number. What's the square root of 16? 4. The square root of 3 of 9. 3. Sorry. My brain is faster than my hands. Plus or minus 4 over 3. Log base 16 of x is equal to 3/4. How could we rewrite that as an exponential? (16 to the 3/4) equals x. Oh, well, that's nice because x is by itself already. All I got to work out is what 16 to the 3/4. Well, I know 16 is 2 to the 4th power. And 3/4 times 4 is 3. So that's 2 to the 3rd. What's 2 to the 3rd? 8. So that's doing it without a calculator. You could type that into the calculator if you wanted to. It'd punch out 8. Being able to rewrite them can solve us some problems. Okay. Log base 36 of the square root of 6 equals x. It's kind of ugly, but doable. Let's rewrite it as an exponential. What's the base? 36 to the x equals the square root of 6. Square root could be written as an exponent. How? 1 over 2. 6 to the 1/2. Right? Can 36 be written as 6 to a power? It's what? 6 squared. So that's really 6 to the 2x equals 6 to the 1/2. And what do we know about if the bases are the same, 6 and 6, what do we know about the exponents? You can add them because there's an equal sign between them. If the base, if this is equal to that, then what do I know about 2x and 1/2? They better equal each other, right? So I'm going to set 2x equal to 1/2. I'm going to divide by 2. If you take half of a half, what do you get? A fourth. X is 1/4. All through rewriting it as an exponential. So we had log base 4 of x is equal to 5 over 2. the base? 4. Exponent. 5 over 2 equals x. X is already by itself, so that means all I have to do is work out this side. What's 4 to the 5 over 2 power? 32. You could do it. 4 is 2 squared. 5 over 2. If you're trying to do it without a calculator, that'd be 2 to the 5th, which is where the 32 comes from, because the 2's cancel each other. On the exponents do. Or you could just type in 4 to the 5 over 2 power. Same thing. Nice when it works out to be a good number. Here's a fun one. Log base square root of 7, 49 equals x. What's the base? Exponent? X. Square root of 7 to the x power is equal to 49. Again, what's a square root? 1/2 power. 7 to the 1/2 to the x is 49. That'd be 7 to the 1/2 x. 49 could be written as 7 squared. So 1/2 x has to equal 2. Multiply by the reciprocal. X got to be 4. Just working with some exponent stuff. We're done last week. Some radicals and rational exponents. Working with those to solve some equations. All right. All right. The next thing is going to be using properties of logarithms to expand or condense okay. Expand makes stretch it out. Condense means put it as one problem. Okay, this is what you were asking on the expanding and condensing part of logarithm. So let's go over those properties real quick of that. So one of the properties is that log base b of b equals 1. Okay. So that's number one property. So if the base is the same as what you're taking the log of, that's equal to 1. That cancel each other out. It's really what's happening there. Okay, it's like 7 divided by 7. That's what that works as. Okay. Another property is that if you have log base b, or I'm going to use b as the base here. It doesn't matter what base the log is. It can be base 2. It could be base 816. It doesn't matter what base it is. These properties hold true for every log function. Okay. If you had a number or something to a power, so like a to the nth power, that property is that n can come down to the front and multiply times log base b of a. So whatever this exponent is on what you're taking the log of, it comes down to the front and becomes multiplication in the front. The exponent can move to the front and be multiplication. Exponents can move to the front and be multiplication. So that's a handy one for expanding or condensing, either one. Let's say you're taking the log of two things that are multiplied together. If two things are multiplied together, think about logs in terms of what they are. They're exponents. Logs are exponents. If things are multiplied together with the same base, what's the rule for exponents? Like x squared times x cubed. What do you do with the exponents? Think x squared times x cubed. What's that turn into? X to the 5 power, right? Because you add them. Okay, so here, logs, multiplication becomes addition. When you're multiplying on the inside of the log, you can split that apart and make addition problem. So multiplication becomes addition. What do you think division becomes? Subtraction. Log base b of m minus log base b of n. It's always top minus bottom. Always top minus bottom. Right. Let's see if we can expand some. Take a single log and stretch it out. And then we'll go the other direction. The expanding helps you learn the properties. The condensing is what we're going to use to help us solve equations later on. Okay? So the expanding helps us learn those rules. The condensing is what we'll actually need to be able to do in order to solve a problem. Okay? So let's see if we can expand. Completely. Expand the logarithm completely. What letter are we on here? N. Log base 7 of 8x. We're going to take that single log and expand it using those properties. So we look at what we're taking the log of. What's going on between the step here? 8 and x. They're multiplying. Multiplication in logarithms turns into addition. Log base 7 of 8 plus log base 7 of x. And you've expanded that logarithm completely. Log base 6 of yz. What's going on between the y and the z? Multiplication, so that turns into log base 6 of y plus log base 6 of z. Log of 15 over 7. How does that expand? Subtraction. So it'd be log of 15 plus log 7. What base are those logs? Okay, that's good. Just checking. Log base 3 of x to the 4th. Well, what are we taking the log of? X to a power, right? That first or second property we talked about, where's this exponent? Where can it go? To the front. Okay. So it's just going to be 4 times log base 3 of x. Nothing else to do on that one. Just bring that exponent down to the front. That's going to be a helpful one. They're all helpful, but that one seems to come up a lot. So we had log base 2 of x to the third y to the 5th. 2 of them in there that we're taking the log of. So we're combining a couple of properties at the same time here. What's going on between the x cubed and the y to the 5th? Multiplication. So that's going to split into what? Addition. What about the exponents on the x and the y? Yeah, they're going to drop down to the front using that property. So it'll be 3 log base 2 of x plus 5 log base 2 of y. Log base 4 of the cubed root of x squared. These are a little bit more difficult because of the cubed root in there makes it tough. But can I rewrite a cubed root as an exponent? So this would be, what was that, Paul? 2/3. X squared inside. So that's the index is a 3. So log base 4 of x to the 2/3. That makes this problem a lot like than cube, right? Because it's just an x to a power, right? It just happens to be a fraction power. Doesn't really matter. What does the 2/3 do? Drops to the front. And then you just log 2/3 log base 4 of x. And so being able to swap from a radical expression into a rational exponent is helpful in expanding and condensing logs. Really, really helpful there. Okay. Let's say we had log base 5 of x squared, the 4th root of y cubed. What do we know is happening here? Say that again. Multiplication. So that means it's going to turn into addition, right? So there's multiplication going on between those two pieces. So we know that x squared is going to split apart and be log base 5 I'm going to put the x. What can I do with the 2? I can put it in the front because it's an exponent, right? And the rule is that if the exponent's there, I can drop it to the front. And then that's going to be plus log base 5. Technically, it's the 4th root of y cubed. But what do we know that this really turns into? Y to the what? Yeah, this is really y to the 3/4. It does not look like 3/4. 3/4. What can the 3/4 do? Go to the front. So 3/4 y. log base 7 x over y to the 5th. So that's what? That's division, so it turns into subtraction. It's going to be log base 7 of x minus what? 5 log base 7 of log base 7, 5 log base 7 of y. This one will be fun. Log base 8 of x y squared z over w cubed v to the 5th. Yowza. So quite a bit going on with this one to expand. The big thing that's happening though is what? The division is the big thing. Okay, so you got all of this stuff divided by all that stuff. Okay, so that right there is going to create a what kind of problem? Subtraction problem. Okay, so division creates subtraction, and so maybe we can do it step by step. So I've split it apart from a division problem into a subtraction problem. Now, I pretend this part's not here and work on this. What does this expand to be? Okay, so that first one expands to be that stuff. That's the first one. Minus 3 log 8 of w. Yeah. Yeah. This would be one way of doing that. You could distribute the minus sign to both of those and have minus 3 log w minus 5 log v. It'd be the same thing. This is correct. Distributing that minus sign to where it's minus 3 log 8w minus 5 log 8v is equivalent. You know, that could, you could do either of those on that end. I would take that. To me, makes good sense. But the underneath that makes good sense too. So it's just distributing a negative. It's nothing incredible out of that. Don't get much more complicated than that, honestly, in expansion. Okay. So that's expansion using those properties. Let's condense some. And this is actually, you know, doing the expanding helps you learn all those rules. The condensing is actually the skill you're going to use to solve some problems with logarithms involved. So we're going to condense. You might see this, the instructions say write as a single logarithm. That may be what they say. I call it condensing because like condense soup, you just condense it. right, so example W, log base 4 of x minus log base 4 of y. We're going to condense that into one single log. The bases have to be the same with the logs for us to condense them together. The bases of the logs are the same. What does subtraction come from? Division. So what's on the top of the division? X. So log base 4 of x divided by y. And that's it. Let's throw a little bit more at it. So 3 of them there. I see plus signs, I see minus signs. Plus signs do what? Multiply. Minus signs divide. Okay, well, okay. We got a problem then. Which one happens first? Why? Because that's exactly right, because it's in front. Remember, order of operations says multiplication, division, left to right, or addition, subtraction, left to right. So because this is in front, it happens first. So what are we multiplying together here? X to the third, y to the fourth. So we have log base 2, x to the third, y to the fourth. So I'm thinking this may be a step that you don't have to write down. Then I've condensed these first two into this. Right? Because it came first, right? Now, minus log base 2 of W. What's that going to do? Division, yeah, by W. So we end up with log base 2 of x cubed y to the fourth divided by W. We condense it down to one log. I don't know that there'd be much we could do with that as an equation because there's too many variables, but the idea of condensing is the key to working some of these problems later on. 4 log base 7 of r minus 5 log base 7 of x. Maybe a little simpler. All right. What's it going to turn into? R to the fourth over x to the fifth. Good job. Real simple. One subtraction problem turns into one division. The exponent rule, you know, shoot those up there to the top. That's what that does. All right. One third log base 5 of x is 2/3 log base 5 of y minus log base 5 of w minus log base 5 of z. Four of them going. Much in the same way we did the one before that had 3 of them. You got to think, what comes first? That's multiplication, right? Because the addition is in the front, right? So log base 5 of what? Say it again. Yeah, cube root of x. Yeah, that's one way to write it. I'm going to write it x to the 1/3 first, and then at the end we'll convert them all to the roots too. I'm just going to write it. And then what else? Cube root of y squared is true. I'm going to write it as y to the 2/3. We'll see why in just a minute while I wait on the cubic root. Paul said over WZ. Why is he saying over WZ? What's happening with both of these? They're both subtracted, right? And both of them being subtracted means that they're put together in the denominator by really multiplication in the denominator. But dividing by W and dividing by Z is just like dividing all of this by WZ. That's a correct answer. This is also correct. Now, Michael, the reason I wait to do that at the end is because both of them ended up being cube roots. And because they're both cube roots, I can put both of them underneath one cube root instead of having 2 separate cube roots there. So I wait to do that at the end because I can see, oh, I got the same denominator, so I can use the same root to get that. If the denominators weren't the same, I would be stuck with 2 separate roots. But because the denominators are the same, I can put them both under the same root out of that. If one was a 1/2 power and the other a cube root, a square root and a cube root don't mix together like that. You got to just leave them separate. So here, since they're both cube roots, you can rewrite it like this. I would accept this, but understand this is the same thing. It says the same thing. It's condensed to 1 log, though. That's the key, is you're condensing these things down to 1 log. Writing it as a single logarithm. That's the key. Okay. All right, last thing in this section is using a calculator a little bit. Evaluate with a calculator. Well, that was letter Z, so we're on A. Log of 49. We're going to get a decimal approximation. On your graphing calculator, down here on the left-hand side, you've got a log button. That's log base 10. Okay, that's the log base 10 button. That's what I'm asking you to find here is log base 10 of 49. Okay, to find the log base 10 of 49, you hit log and then 49. That finds you log base 10. We're going to go 4 decimal places. So 4 decimal places goes to the 1. We look at the number after that. It's a 9, so that makes this 1.6902. Round it up. Log base 10 is easy to find. Natural log. On your graphing calculator, you got a natural log button. Down that first column, down here, 3rd button up, from the on, 2nd button from on, LN. Okay. To find the natural log of 6, you just hit LN of 6. And again, we're going 4 decimal places. So 1, 2, 3, 4. Look at the 5 afterwards. So that's going to be 1.7918. 5 and up goes up. Copy that, right? Yeah. Okay. When it's one of those are called common logs. Common logs, you have a button on your calculator to use. The other logs, the base 2 and base 3 logs, those are a little more difficult to do on the calculator, but I'm going to show you how, because it'll do them. If you've got the newer operating system, it does them really in a neat way. Log base 2 of 15. To get the log base with your calculator, there's a couple of different ways to do it. I'm going to show you the way that I usually do. I hit the math button and press up until I get to that thing that says log base. Okay. We'll hit enter. If yours doesn't come up looking like this, then we're going to do it a different way. And I'll show you that in just a second. Is there anybody's that doesn't come up like this? It's okay if it doesn't. I'm going to show you another way anyway, whether everybody's does or not. Okay. Log, this is the base of that. So for our problem, we're going to put a 2 right there in that box and a 15 right there. So put a 2, then press the right arrow key, get you in the other box. We'll put a 15. 3.9069. If you can't get the log base to work, or you don't have your graphing calculator with you, and all you've got is just a regular scientific or the calculator on your phone. Like if you're using an iPhone, you can turn it sideways. It gives you the more multifunction scientific calculator style, and there's a log button on there. It doesn't have a log base button. It has a log button. You can do log base 2 using the regular calculator by doing log base 10 of 15 divided by log base 2. So if I did log 15 divided by log 2, and you got to close the parentheses there on that. Hit enter. I get the exact same decimal they got here. And it works the same way. This is called the change of base formula, and used to be the only way we could do it with the calculator is with the change of base formula. Now they've gotten smarter with the technology and reprogrammed these calculators that they can handle typing it in this way. It calculates it the exact same way. That's why it's funny. It just calls them different. But log of the big over log of the base. The base is in the bottom. That's the way I always remember that. The base is in the bottom. So if your calculator for some reason won't let you do this, or you can't remember where to find that, log of the base on the bottom, log of the other number on the top, and that'll get you the same answer. It's called the change of base formula. Okay, so being able to evaluate some logs with the calculator, handy thing to do. Go to the next section. All right. A lot of stuff. It's a pretty short section here. Just very few examples here. Actually, 2. Section 4.4. A quick application of logs. pH. It's about to get pool season. And the pH value of the water in the pools is very important. Bacteria from growing. Which chlorine do you need and all that stuff based on the pH values of your pool water. All right, so pH is calculated using a log of the number of, what is that called? Hydrogenized oxygen. It's not water because H2O is water. Hydrogenized oxygen ions is what that is. But this is the number of those ions, okay? And this stuff's they're gonna give you this information out of that. But you're gonna find the pH or find how many ions there will be based on that. So let's take the first example. We're gonna find the pH when the count of the H3O ion is 2.5 times 10 to the negative fourth. That's how many there are per parts per million. Isn't that how pool water is measured, parts per million? So the pH, again, is the negative log of that number, 2.5 times 10 to the negative fourth. So all we got to be able to do is type that into the calculator. All right? So I would go to my calculator and I would type negative log 2.5 times 10 raised to the negative 4. Close the parentheses. Hit enter. We go 4 decimal places. Be 3.6021. pH. 7's neutral, isn't it? pH. 7's neutral. Alkaline and acidic. Acidic goes toward 1. Alkaline is bigger numbers, right? Is that right? It's been a while since I've done the science part of this. The math part I've done a lot of, but I haven't done a lot of the science part. I can't remember. Basic, more basic it is, the higher the number it is. Okay, so this would say our water is pretty acidic. Might turn your hair through. Ever had it seen that? I had a friend that his did that all the time. It was hilarious. We would push him in the pool if we knew it was the right, knew the water wasn't ready. We pushed because his hair would turn green. It was funny. He didn't think it was funny. It was funny to us. So if the pH equals 7.1, find the count on those ions. So here, this is a solving exercise. Okay, so this is going to involve the idea of rewriting a logarithm as an exponential in order to work this out. So if the pH is 7.1, remember the pH is the negative log of the number of H3O ions. Okay, so if we know the pH is 7.1, we know that water is pretty neutral. It's perfect. 7.0 would be perfect. 7.1 is really, I don't think you can get any better than that, honestly. You get to adjusting too much with that, it'd mess it up. So we have negative log of, and I'm just going to put an X in there because rewriting this junk over and over just gets old. So I'm just going to change that to X. Okay. So what's in front of the log there? A -1, right? So how could I get rid of that? Or divide it by -1. It gets the same result. Multiplying by -1 works, but I'm going to divide because they're already multiplying. So the opposite of that would be division, just to keep that idea in our head. So that's -7.1 equals log of X. Now, we got a logarithmic statement here. Could we rewrite that as an exponential and figure out what X is? What base is the log? 10. How do we know that? Because it doesn't have anything there, right? Because it's a common log base 10. So if I'm going to rewrite that X as an exponential, it'd be what? What's the base? What's the exponent? Remember, a log is equal to a exponent. So if 10 is the base, what's the log equal to? Negative 7.1. So that's the exponent. So x has got to be over here. Oh, wait. That's the number. That's what x is. By just rewriting, we didn't actually do much calculation dividing by -1, but what's that? That's nothing. Without doing any calculations there, just rewriting it as an exponential, we found out what x was. We found out x was 10 to the negative 7.1. I'm just going to 10 raised to the negative 7.1. All right. That's an ugly number, but that's okay. We're going to rewrite it in scientific notation. 7.9433. 7.9433 times 10 to the negative 8. I'm getting that from here. This E symbol in your calculator means times 10 to this power. So it's like scientific notation in your calculator. So I just typed in 10 to the negative 7.1 and hit enter. Okay. Spit me this back out. That's what I want to do to find that pH level. Okay. All right. Already done those. Let's go to 4, 5. All right. Exponential and logarithmic equations. What you got to understand here when we start doing these equations is that in order to solve an exponential equation, you're going to use a log. In order to solve a logarithmic equation, you're going to use an exponential. Okay? They're inverses of one another. It's kind of like in order to solve a multiplication problem, you use a division because they're opposites of one another, they're inverses of one another. It's the same thing here with exponentials and logarithms. Okay, so let's look at an example. 8 to the x equals 21. What kind of equation would you call that? You describe that as an exponential because it doesn't have what in it? It doesn't have any logs in it, right? So it's an exponential equation. Now, earlier, like last week, we were talking about exponentials. We were doing some equations, and we would try to get the bases the same on each side. The reason we're not doing that today is because can I turn a 21 into an 8? 21 is 7 times 3. There's no way to turn 21 into the same thing I can turn an 8 into. I can turn 8 into 2 cubed, but there's no way to turn a 21 into 2 to a power. That's the reason we've got to use logs to solve these, okay? Now, the beautiful thing about this is it really doesn't matter what log base we use to solve this. This textbook and most college algebra textbooks that I've worked with over the last 11 years of teaching use a natural log. I guess just because it's shorter to write and you've got a button for it on your calculator. Okay? You technically can use any log base you want to, but we're going to use natural log to solve this. Okay? Now, this is where some of the properties of condensing and all that stuff come into play. So here's how we're going to solve this. We've got the part that has the exponent by itself, 8 to the x. We didn't have to do anything to get it there. There'll be some where we got to do a little bit of work. So we don't have to do anything to get it. I'm going to take the natural log of both sides. Okay? So I'm taking natural log of 8 to the x equals the natural log of 21. Okay? That in itself really doesn't do anything. But what that allows us to do is do what with this exponent? Where? In front of the ln, so it becomes x times the natural log of 8. Which then creates a problem we can solve. Okay? This x can drop down here and get x times the natural log of 8. Here's what you've got to know. Natural log of 21, what is that? Is it a pumpkin? Is it an Easter egg? Or is it a number? It's a number. Natural log of 8 is just a number. It's a decimal number that's real ugly, but it's a number. Okay? So this problem is no different than a problem like this. 7x equals 14. How do you solve 7x equals 14? How do you get x by itself? You divide by the number that's multiplied times x, right? For this problem, this is the number that's times x. So we're going to divide by that number. This side, they cancel out. There's x by itself. The exact solution is natural log of 21 divided by natural log of 8. We're going to get a decimal approximation for that as well. Okay. The good thing about using natural log is we don't have to go hunt the log-based thing to use. So with the calculator, I'm just going to do natural log of 21, close parentheses, divided by natural log of 8, close parentheses, enter. Going 4 decimal places, same as we've done all night, 4 decimal places. 1.4641. All of that is the answer. Some of the questions on your Canvas quiz and on the regular test will be exact solution. Some will be asking for decimal approximation. So be able to do both. 11 to the x equals 32. It's a very similar problem. What do we do to solve this one? Take the natural log of both sides. What happens to the x? Drops to the front. Divide by natural log of 11. Natural log of 32 over natural log of 11. And let's get the decimal approximation for that. .4453. Okay. So, single term on the left, single term on the right. Take the natural log, get the x out of the exponent. That's the key, getting the x out of the exponent. Right? Now, what if there's a little bit more involved? Thanks, sir. Have a good week. So, maybe we got something like 5 to the 2x plus 1 equals 6. Yeah. Is this much different than A and B? Not much. The only difference is the exponent's a little bit bigger. Got more stuff in it. So what do we do to get that stuff out of the exponent area? Take the natural log both sides. That lets us get 2x plus 1 times the natural log of 5 equals the natural log of 6. Now, there's a couple of different ways to work with this. One would be, what does this look like you could do? Distributive property. That's one way to go about it. And it works. You're going to get the same answer, your equivalent answer. It's going to look a little different. But by distributing natural log of 5, you're going to end up in more places that have natural log of 5 on it, right? We don't have to do this one that way. What's going on between this big piece and this now? They're multiplying. So I can undo that by doing what? Division. Which part of that is just a plain number? One's a number, but which part of the multiplication? This part has got an x in it, right? This part does not. So this is just a regular number. If I just divide by this, it'll get the ln5 out of the way. And all I have left on that side is 2x plus 1. So that's what I'm going to do. I'm going to divide by the natural log 5. That'll leave me 2x plus 1 equals natural log of 6 divided by natural log of 5. This little ugly thing right here, that's a number. It's not a pretty number. It's a big long decimal that we couldn't write all the digits to. We're just going to leave it as that fraction right now. How do I get x by itself over here? Subtract 1 first. So that's going to give me 2x is equal to natural log of 6 divided by natural log of 5 minus 1. And then one more step gets x by itself. That again? Divide everybody by 2. So if I divide this one by 2, I got to divide that one by 2 and that one by 2. Not pretty, but it sure got x by itself, right? If I divide by something into a fraction, it just becomes part of the denominator. And then all I've got to do is get a decimal approximation. So dividing by 2 just puts the 2 in the denominator of that. And then get a decimal approximation for that. So natural log of 6 divided by 2 times the natural log of 5. Notice that I put the denominator all in parentheses because it matters. If you don't, you're going to get it wrong. And then minus 1/2. Going 4 decimal places. 1, 2, 3, 4. So 0.0566. What x is equal to. All right. So that one not distributing makes it a little bit shorter. Not a whole lot shorter, but it did save us the headache of having to deal with the natural log of 5 in more than one place. We only had to have it in one place. All right. Now let's look at one that's a little bit more complicated. 5 to the 2x minus 3 equals 8 to the x plus 1. Now, this one has x's on both sides in the exponent, which is not a fun thing. Makes it much more a much more difficult problem because x is in more than one place. So, how do we get those x's out of the exponent? Take the natural logs of both sides. So that's going to give us 2x minus 3, natural log of 5 again, and then we're going to get x plus 1, natural log of 8. Now, on this one, we don't have the luxury of not distributing because there's x's on both sides. If there wasn't an x over here, we could just do that trick where we just divide by the natural log and go get it over there and get it out of the way. But because there's an x over here, we can't do that. So we're going to have to distribute both of these on each side. Okay? That makes this problem a little bit longer, a little bit tougher. Okay, so what's that turn into? When I distribute natural log of 5 to 2x, that's just going to be 2x, natural log of 5, minus 3, natural log of 5. On the other side, that's just going to be x, natural log of 8, plus 1, or 1 times natural log of 8 is just natural log of 8. I don't even have to put the 1 there. Makes it a little shorter. Now, what am I solving for? I'm trying to get by itself. X. What has x on? This piece and this piece, right? Where do they need to be? On the same side, right? Because remember we did problems, easy problems, where you had like 3x plus 5 is equal to 2x minus 7. You had to get your x's on the same side. It's the same idea here, even though it's got the natural log stuff in there. Okay? So I'm going to subtract x natural log of 8 to get that one away from this other side. And then I'm going to add 3 natural log of 5 over here. So that I get rid of this piece that doesn't even have x's. Get over here with this other piece that doesn't have x's. Okay? So that's going to give me 2x natural log of 5 minus x natural log of 8 equals natural log of 8 plus 3 natural log of 5. Ooh, doggies, that's a lot of stuff. But we're just 2 steps away from getting the answer. Now, I could not combine these two because this is natural log of 5, that's natural log of 8. They're not the same. So I couldn't just put them together. But what do they have in common? Both got x's, right? So that would be like a greatest common factor on them, right? So if I pull the x out with the GCF, I'm not doing anything to the other side. I'm just copying it down. What's left inside those parentheses there if I pull the x off of both of those? Agree with that part. 2 natural log of 5. Because this 2 that's right here is still there. I didn't pull a 2 out. I just pulled the x off of it. So now, what do we know about this stuff in the parentheses here? What kind of thing is it? Is it a piñata? Is it a number? It's just a number. It's a weird looking number, but it's a number. It's a number times what? Times x. And if they're multiplying together, the way to undo that is divide by what? That what? What is that? That number, right? I'm going to divide by this number to get x by itself. minus. So x equals the natural log of 8 plus 3 natural log of 5 divided by 2 natural log of 5 minus natural log of 8. Or as a decimal. So this is where the fun part is. Natural log, parentheses, natural log of 8 plus 3 natural log of 5. Close those parentheses up, divided by parentheses 2 natural log of 5 minus natural log of 8. Close those parentheses up. 6 point, going 4 decimal places, 0624. I'll be honest with you. I think these kind may be the hardest ones that we do all in the whole, not just this chapter. Just because it's so hard to get out of your brain that natural log of 5 is just a number. Because it looks like something else, but it's just a number. Okay. Let's look at this one. Let's go to a little lighter problem. Not quite as difficult, but still challenging. E to the 4x, e to the x minus 1 equals 5e. Okay. Now, this is one of those where we want to do some exponent rules first because you've got two pieces that have the same base on the same side. What's the rule for those exponents when you multiply things with the same base? What do you do with the exponents? You add 4x plus x plus 1. That would be e to the x plus 4x would be 5x minus 1. Now we have something with an e on the left side. We have a 5e on the right side. 5e is just a number. It's 5 times 2.71 and some change. That's what that means. Okay? It's just a number. So how do I get that exponent down? How do I get it in front? What do I have to do to both sides to get it there? Take the natural log, right? And here's a beautiful thing that happens. The natural log of e, what's natural log e? It's log base what? E. Log base e of e does what to itself? Cancels itself out. So really, this part is gone. And we have 5x minus 1 equals natural log of 5e. And, you know, I could do a little work there with that part. Because that's a multiplication problem inside of a log. So how could I expand that? I could make it natural log of 5 plus natural log of e. And what does natural log of e do again? And turns into what? Turns it, this one, it kind of went away, but it's actually turning into what? 1. So this is actually natural log of 5 plus 1. Now, let's get x by itself. What's the first move to get x by itself? Gotta get rid of that 1, right? So if I add 1, I got a like term to add it to. So that's natural log of 5 plus 2 now equals 5x. And how do I get x by itself? Everybody gets divided by 5. So x equals natural log of 5 over 5 plus 2/5. We're going to get the decimal approximation for that. Natural log of 5 divided by 5 plus 2 divided by 5. 0.7219. That one, neat little trick. The expansion gets some canceling. If you didn't expand that, you still get the same decimal approximation. Your exact answer would look just slightly different. Not much different, though. Be slightly different. Okay. All right, let's look at some problems that start with a log inside of them. Everything we've done so far has had exponents. It's exponential. Let's get some logarithmic things going here and see what we can do with that. And go from there. All right. What letter are we on here? F. 4 natural log of x equals 36. The key to doing these problems is getting the log part by itself, whatever log base it is. Get that part by itself. Okay, so right now that 4 is attached to the front of that log, natural log of x. It's 4 times natural log of x. How can I get rid of that 4? If I divide by 4, it'll get rid of it, right? So that's what we'll do. So that gets me natural log of x equals 9. Now, I mentioned this earlier, that in order to solve an exponential problem, we use the log. In order to solve a log problem, we're going to use what? Exponential. What base is this? E. That's the base we're going to exponentiate with. Okay, when I say exponentiate, what I mean is you're going to make the base of whatever log is in the problem. Here we got a natural log. So the base is going to become E on both sides. Here's the beauty of that. When you do the base being E, this little symbol here is just a caret symbol saying this becomes an exponent. This becomes an exponent. E raised to the ln of x, the ln and the E cancel each other out. So when you use the base of that log to exponentiate, they cancel one another out. So that leaves x to be e to the 9th power. And we're going to get a decimal approximation for e to the 9th power. To do that, you hit second ln, that gets you the e, and then the 9th power. Second ln to get the e, and then you put the 9th power with it. 8,103, we'll go 4 decimal places again. So 0.0839. $103.0839. Right? do this one. Log base 3 of x plus 6 is equal to 5. Okay? So we have a log base 3 in this problem. Is there anything like on the outside of that log? The first one had a 4 in front. There's nothing in front, right? There's nothing added on the end out here that we need to do. So the log is by itself. We want to exponentiate. Once you have the log by itself, we want to exponentiate with the base of the log. What's the base of this log? 3. So we're going to exponentiate with a 3. What happens to the log base 3 and the 3? They cancel each other. That leaves me x plus 6 is equal to 3 to the 5th power. What is 3 to the 5th power? Is it a number? What number? 243. So we really just have a regular problem now. X plus 6 equals 243. How do you get x by itself? Subtract 6. 237. That's what x is. Well, that's handy. Let's throw in a little bit of those log properties and how they can help us. Log base 2 of x plus 4 and then squared is equal to 24. What is what's one of the log properties that I could use here to make this problem a little bit better? Yeah, that log exponent rule that drops that 2 down to the front, right? 2 log base 2 of x plus 4 equals 24. Okay. Now, what can I do to get rid of this 2 that we put in the front? I can divide by it. That gives us log base 2 of x plus 4 equals 12. Now, how do I get rid of the log base 2? Exponentiate with the base of 2. X plus 4 is 2 to the 12th. It's applied to both sides. It cancels out. It can't get to it because the log base 2 and the 2 with the exponent cancel each other out. Yeah, it breaks that down. It's kind of like the square root of something squared. Like if I had x plus 4 squared inside of here, I can't take the square root of anything inside the parentheses because this cancels that. It's the same idea. It's just with logs and exponents. Exact same idea.
You raise the log down.
Because it's not multiplication that's going on between that log. It's the log base 2 of x plus 4. So it's not log base 2 times x plus 4. It's log base 2 of, which is like a function type. Okay. What's 2 to the 12th power? Might have got that. 4,096. And then subtract 4. 4,092. What x is? That worked out nice. So getting the log by itself, definitely helpful. Okay. And then exponentiate. Log of 2x plus 1 plus log of x equals log of x plus 8. This one has logs everywhere. So the left side's got 2 logs on it. Could we combine those? How? Yes, you can, but how do you do it? Adding becomes what in logarithms? Multiplication. So if we combine those two, it's going to turn into log of x times 2x plus 1, which would be 2x squared plus x. Okay. Now, they're the same logs on each side. So what will get rid of those logs? Say that again? 10. An exponentiation with a 10 as the base. They cancel out the logs, leaving us 2x squared plus x equals x plus 8. Now we got to solve that equation. Has to equal 0 because it has what in it? X squared in it makes us have to get it equal to 0. So I'm just going to move these over here. There's the equal 0. I have 2x squared. The x's cancel each other out, and minus 8 there. 2x squared minus 8 is equal to 0. Well, that's nice when it does that, because that means now I can get x squared by itself and then take square roots and get the answer. That's a quicker method than factoring could be. So I'm going to do that. I'm going to add 8 back. And then I'm going to divide by 2. And that works real nice because now I got 4. And I know how to take the square root of 4 pretty good. What's the square root of 4? Plus or minus 2. We got 2 answers. We got x equals positive 2 and x equals negative 2. When we get more than one answer, now technically we're supposed to do this even when we only get one answer. We should check our solutions to make sure they work. Here are the rules for when they don't work. You can't take the log of a negative number. So, if I put in a 2 in the original problem, go back all the way to the original, back to the top. If I plug in positive 2, positive 2 times 2 is 4, plus 1 is 5. That's positive. It's good there. Plug it in here. Log base 10 of positive 2. We're good. Plug it in here. 2 plus 8 is 10. Log base 10 of 10 works. That works. Okay? If I go and plug in a negative 2, if I plug in negative 2 right here, 2 times negative 2 is negative 4 plus 1 is, I cannot take the log of negative 3. There's no way that I can have 10 to a power and it equal a negative number. There's no way that happens. So the negative 2 is what's called an extraneous solution. It's extra. We throw it out. We show that we found it, but we throw it out. Okay. Technically, we're supposed to check them all, but usually we don't. That doesn't come up until you get more than one that you need to check them. Okay. Let's look at another one here. What are we on, J? log base 3, 4x plus 1 minus log base 3 of x plus 1 equals negative 3. Okay. What can I do maybe to condense those logs on the left side? There's two of them there on one side. That's when you want to think, how can I put them together and get one log so I can get rid of the log? What's going on between them? Subtraction. And that comes division. So that's going to be log base 3 of 4x plus 1 over x plus 1. How do I get rid of the log base 3? Exponentiate with a 3. I got 3 to a negative 3. That's 4x plus 1. These cancel out. That's what I want to happen. What's 3 to the negative third power? And I 3 raised to the negative 3. And I'm going to change it to a fraction. 1 over 27. The reason I want to change it to a fraction is because I don't want a repeating decimal happening there. If I round that at all, it's not going to give me the right answer at the end. You don't ever want to round an answer or a number until the very end of the problem. Now, this looks a lot like what kind of problem? Starts with a P. Ends with a proportion. Yeah. Oh, how do you solve proportions? I remember doing that many moons ago in a geometry class, maybe, or algebra 1, 7th grade math. Cross multiply. Bottom times top. 1 times x plus 1, x plus 1. 27 times, so technically this is what's happening. That I'm cross multiplying bottom times top, bottom times top. And it's just distributive property for this. So 1 times x and 1 times 1 just gives me x plus 1 on that side. Which is nice. On the other side, it's not quite as pretty because I got 27 times 4, which would be 80 plus 28, which would be 108. Plus 27. Now that problem is not too difficult to solve, right? How do we do it? Get the x's on the same side. That's absolutely right. So I'm going to subtract x. I'm going to subtract 27. That's negative 26 equals negative, positive 107x. Now what? Divide. Last step is divide by 107. So x equals negative 26 over 107. I got a negative answer. Does that mean I throw it out? Even though I only got 1, it's possible that you do throw it out. How do you know for sure? Plug it into the original problem. See if it gives you a negative inside of a log. I'm going to think, what's negative 26 over 107? That's about negative 1/4. It's close to it, right? So we're just getting a good estimate there. You can type it in with a calculator if you want to. That's probably the better solution to do that. So we're going to say 4 times negative 26 divided by 107, and then plus 1. Is that a positive number or a negative number? Positive. So that part of the log is okay. Go to the next piece. Negative 26 over 1 over 7 plus 1. That's a positive number as well. So I get the log of a positive number in both spots where there was a log. So that means I keep this answer. Yeah, I don't throw it out. It's a keeper. All right. Fun. Let's do one more of these. One that kind of gets a quadratic involved. They come up some. Log base 2 of 2x minus 5 plus log base 2 of x minus 3 equals 3. What do? Similar to the last 2 or 3 we've done. So. All right, so they're adding, so it becomes multiplication. Very good. So we're going to multiply 2x minus 5 times x minus 3. So I got to multiply that out. 2x times x is 2x squared minus 6x minus 5x plus 15. So that's going to be log base 2 of 2x squared minus 11x plus 15 is equal to 3. Good job. It turns addition, turns into that multiplication, and then just got to do a little bit of algebra there, multiplying it together. Okay. Now what? Exponentiate with the 2 because it's log base 2, right? So 2 has a base. These cancel. There's that quadratic left over. 2 to the third power. 2 times 2 is 4 times 2 is 8. Okay. Subtract 8 to get it equal to what? 0, because we got to have it equal to 0 in order to solve a quadratic. That's 2x squared minus 11x plus 7 equals 0. Now, how do we solve that? Because it's a quadratic. I need it equal to 0 in order to solve it. Because it's got the x squared on it. If it didn't have the x squared, I wouldn't have to have that. But we could try x method. So x 14 add to be negative 11. So negative 7, negative 2 gets negative 9. That doesn't work. Negative 14, negative 1 gets negative 15. That doesn't work either. That's the only options I have for multiplying to be 14 and adding to be negative 11. So it won't factor. So I have to use what? Quadratic formula. Remember quadratic formula? X equals negative b plus or minus radical b squared minus 4ac divided by 2a. Okay. A is the number in front of x squared, b is the number in front of x, and c is the 7 on the end down there. Okay, so we're just plugging those things in. Negative b, the opposite of negative 11, is positive 11. Negative 11 squared, not plus, but minus 4 times A times C. All that's divided by 2 times A. So we're just going to work this out. 11 plus or minus square root 11 squared, 121. 4 times 2 is 8. 8 times 7 is 56. 121 minus 56, 65. 4. Yeah. Square root of 65 is not a pretty number. It's not nice. So we're just going to leave it the square root of 65. And we're going to get decimal approximations for these. 11 plus the square root of 65 divided by 4. And x equals 11 minus the square root of 65 divided by 4. Okay. So 11 plus the square root of 65. Oops, I don't know why I did that. Enter. Then divide that by 4. 4.7656. 7656. And then the 11 minus the square root 65 divided by 4. 0.7344. All right. Now, both positive answers. The question is, do both of them work in the original problem? And in the original problem, we've got 2x minus 5. So if we just take rough estimates of these numbers and plug them in here, 2 times 4 is 8. 8 minus 5 is 3. So that's a positive number. 4 minus 3 is a positive number, right? So the positive, the 4.7 whatever, it works. We're for sure keeping it. So I'm check mark by that. Now, 0.7344, if I double that, if I have 75 cents and I double it, I got $1.50, right? $1.50 minus 5 is a negative number, right? So that right there, that just that one log having a negative inside of it means you throw this answer out. Okay. So the only answer we have is that 4.7656 as our solution for that problem. So tough stuff here when you're dealing with good logarithmic problems. Not the easiest of stuff to deal with. Let's look at some problems that you might want to see out of your textbook for these various sections to get you going. All right, so there's the problem set that you want to look at for this section. Things to look for in Canvas this week. Got a quiz, Canvas quiz covering this stuff, and then you'll see a review for the test over this material, at least last week and this week's sections. So from R6, R7, 1.6, 4.2, 4.3, 4.4, 4.5, and 4.6. All those sections, you'll see a review test showing up on Canvas for that to get you ready for that. And you'll see some labs that, and I'll give you some instruction on those when you get those in the email as to what we're going to do with that, because it wasn't your fault that the copies didn't make. Okay, so I won't kill you on those at all. But next week, exam 3, barring anything crazy happening, and just supposed to cancel last night because didn't know what the weather was going to do, but it seemed to clear out before time for me to leave. So just keep it. So next week, exam 3. That means we only have one more exam after that. So we're getting close to the end, and then the final, of course. But that's the end of the night. We're supposed to have an email the picture of your answer. You're welcome. Okay. If you got it with you, or okay, all right, yeah. Try to send it again tonight. I didn't get one unless you sent it. Did you send it today or?
It was yesterday.
Okay, I didn't. Then I know I didn't get it then.